Let us see one application of this result. So I prove the generalized Boole's inequality. Note that Boole's inequality was probability union k is equal to 1 to n ek is less than or equal to summation k is equal to 1 to n probability of ek. This was the Boole's inequality. Here n was finite. I am saying even if n is infinite, if you are taking the union of countably infinite collection, then also this result holds. And the idea is very simple. First I consider Fn, which is union k is equal to 1 to n ek. So this Fn is a union of finite number of sets. As n is increasing, you are taking the union of more and more sets. If you take union of more and more sets, your set increases. So this suggests that Fn is an increasing sequence of sets. And what is the limit of Fn? Limit of Fn would be limit of union n is equal to 1 to infinity Fn. When you are taking Fn, you are going from k is equal to 1 to n. Since it is increasing, it would be same as union k is equal to 1 to infinity ek. So thus, probability union k is equal to 1 to infinity ek, which is same as probability of limit of Fn. But for increasing sequence, we have seen that probability is continuous, so this is same as limit of probability of Fn. Also for n is equal to 1 to so on, probability of Fn is same as probability of union k is equal to 1 to n ek. Now I apply this Boole's inequality, which was for the finite case. This would be less than or equal to summation k is equal to 1 to n probability of ek. This happens for all n. So I take the limit both aside, so limit of probability of Fn will be less than or equal to limit n going to infinity summation k is equal to 1 to n probability of ek, which is same as limit of a partial sum, which is same as the series summation k is equal to 1 to infinity probability of ek. So if you combine now these two, you get probability union k is equal to 1 to infinity ek, which is same as limit probability of Fn, which from here is less than or equal to summation k is equal to 1 to infinity probability of ek. So this proves the generalized Boole's inequality. Now let me introduce a definition. So suppose you have a collection of sets E alpha. Now here S is an index set. So for example, S could be 1, 2, 3, so on. In that case, this collection of events would be E1, E2, E3, and so on. So suppose E alpha, alpha belonging to set, alpha belonging to S is a collection of events. I will say that this collection of events are mutually exclusive if intersection of any of them two is phi. So that means these events do not have anything in common. Now such events are called mutually exclusive events. Now I would say a collection E alpha, alpha belonging to S of events to be exhaustive. So as the name suggests, they are exhaustive. That means they exhaust the whole sample space in certain sense, in probabilistic sense. They may not be whole omega, but their union, if I take the probability, so probability of union is always 1. Of course, this does not imply that union alpha belonging to S, E alpha is omega. So they are exhaustive in the sense that if you take their probability of their union, that turns out to be 1. You will see many such examples where this would not imply that this union is same as omega. It is same thing as saying that probability of E is equal to 1 does not imply that E is equal to omega. That you may have events whose probability is 1, but they are not the same as the sample space. You will see many such examples. Let us come to the equally likely probability models. These are a special kind of a probability models. So suppose my omega is finite, it has k elements, omega 1, omega 2, omega k. Now for a set A, I define mod of A to be the number of distinct elements in A. Now suppose my probability function is such that probability of every singleton is 1 by k. Now 1 by k is important because finally my P of whole omega has to be 1. Now omega consists of omega 1, omega 2, omega k. So omega can be written as union of singleton omega i's. So P of omega would be same as summation probability of omega i's. So if I assume all omega i's are same and I want P of omega to be 1, so each of them has to be 1 by k, and that is the reason why I have taken it to be 1 by k. Now once I have a probabilities for singletons, I can define the probability for any E subset of omega. So that means any event. How do you define? Because E can be written as union of singletons such that omega I belongs to E. Now these singletons are disjoint, so probability of E would be same as summation omega I belonging to E, P of omega I. But each of P of omega I is 1 by K, so this is same as number of elements in A divided by K. So that is what is being done over here. So probability of any event E is same as number of elements in E divided by K, which is coming from here. Now this we call as saying that mod of E as number of cases which are favorable to E. And K is the total number of cases. Now this is clearly a probability function because P of E is greater than or equal to 0, because P of E is number of something divided by number, so it is greater than or equal to 0. Suppose EI is a countable collection of disjoint events. Then I consider what is the probability of union EIs. This is same as number of elements in union divided by total number of elements, which is K. But EIs don't have anything in common. So number of elements in union EIs would be same as if you are counting the elements separately in each of them, because none of the elements would get counted twice. So this is same as sum of elements in individual EIs divided by K. Now this 1 by K is sitting as a constant outside a summation sign. I take this inside. So this becomes summation I belonging to AS mod of EI by K. So it is like that C of A1 plus A2 plus AK is same as C times A1 plus C times A2 and so on. So that is what I have done. 1 by K I have taken inside the summation sign. But this is same as, there is a summation sign beginning over here, summation I belonging to S, P of EI. So it satisfies the second axiom also. Now let's look at the axiom third, which is P of omega. P of omega is mod of omega divided by K. Mod of omega has K elements, so K by K, which is 1. So these are probability functions. So equally probability models are the probability models where omega is finite, and probability of any event E is same as number of cases favorable to E divided by total number of cases. So such models are called equally likely probability models. Now as remark, when we say that a random experiment with finite sample space has been performed, so it is something like that, I say a coin is tossed at random. So when we make such a statement, what it means is all the outcomes are equally likely. For example, when I say a coin is tossed at random, what it means is probability of head is same as probability of tail, which are the two possible outcomes, head and tail. Each probability is 1 by 2. Now we have seen if that is the kind of a probability model which is an equally likely probability model, then P of E is number of cases favorable to E divided by total number of cases. So wherever you have equally likely probability model, you have this expression for the probability. Or whenever you use the terminology that your experiment has been performed at random, then probability of any event E is same as number of cases favorable to E divided by total number of cases. To quickly see this, let us look at one example. Suppose 5 cards are drawn at random and without replacement from a deck of 52 cards. So you have 52 cards, I draw 55 cards at random and without replacement. So that means you cannot get the same card because I have not replaced it back. And I define E1 to be the each card is spade, E2 is at least one card is spade, E3 is 3 cards are king and 2 cards are queen, E4 is 2 kings, 2 queens and 1 jack are drawn. So here again the word at random has been used, so that means it is equally likely probability model. So probability of any event would be number of cases favorable to E divided by total number of cases. So let's look at probability of E1. What is the total number of cases? Total number of cases is because 5 cards are drawn at random and there is no repetition. So that can be done in 52 choose 5 ways. So 5 cards can be drawn from 52 cards in 52 choose 5 ways. Number of cases favorable to E1. E1 is I want each card to be spade. So that means I want all the 5 cards from the collection of 13 spade cards. That can be done in 13 choose 5 ways. So probability of E1 is number of cases favorable to E1, which is 13 choose 5, divided by total number of cases, which is 52 choose 5. Let's look at probability of E2. Probability of E2 is at least one card is spade. Now at least one card is spade, it can happen in 1 card is spade, exactly 2 cards is spade, exactly 3 cards are spade, and then all 5 cards are spade. But for that I'll have to calculate 5 probabilities. I don't want to do that. So rather what I do is I consider its complementary event. What will be a complementary event of at least one card is spade? That means no card is spade. So probability of E2 is same as 1 minus probability of E2 complement, which is same as 1 minus probability that none of the card is a spade. Total number of cases is still 52 choose 5. Now I want none of the card is spade. So that means all the 5 cards are coming from those 39 cards which are not spade. And that I can choose in 39 choose 5 ways. So this is what the probability of E2 is, 1 minus 39 choose 5 divided by 52 choose 5. Now probability of E3 similarly you can find. Total number of ways in which 5 cards can be drawn is 52 choose 5. I want that 3 cards are king. There are 4 kings, so that can be done in 4 choose 3 ways. I want 2 cards are queen. There are 4 queens, so 4 choose 2 ways. So this is what probability of E3 is. Now probability of E4, again total number of ways is 52 choose 5. I want 2 kings, so out of 4 kings, 2 kings can be chosen in 4 choose 2 ways. 2 queens, again 4 queens, out of them 2 have to be chosen, so 4 choose 2 ways. It is by the multiplication law of counting. Then I want 1 jack. So for each of these 1 jack from the 4 jacks, that can be done in 4 choose 1 way. So these are the usual, follows from the usual counting principles. Now I'll use the convention that in many books you'll find that they have used the word an unbiased coin or unbiased die is thrown. Whenever word unbiased comes, what it means is all points are equally likely. Sometimes they will also use a fair coin or a fair die. That also means that all outcomes are equally likely. For example, when I say fair coin, that means probability of head is same as probability of tail, which is half. Fair die means probability of 1 is same as probability of 2, or which is same as probability of getting 6. Each of them is 1 by 6. When we say a coin is loaded or die is loaded, that means all points are not equally likely. So that means some points have more probability of getting observed. So before I conclude, let me give you take-home problems. So suppose my omega is closed interval 0, 1. For any semi-closed interval AB, which is subset of 0 to 1, I define P of AB to be B minus A. Now such a probability function exists. One can prove that such a probability function exists. And suppose S is any countable set. Then find what is the probability of AB, probability of semi-closed interval AB, probability of open interval AB. Also find what is the probability of singleton A. So what is the probability of a singleton point A? And in general, try to find out what is the probability of any countable set S. Now, let me give a hint. You can use, for some of the parts, continuity of probability function. So somehow you have to write down those probabilities in terms of these probabilities, which are known to you. Then second problem, 2 slips are drawn together and at random from a box containing 6 slips. And these slips are numbered 1 to 6. And you have to find the probability that larger of the numbers on drawn slips is 3. So take these 2 as homework problems. Now let me give a summary of things which I'll be doing in the next module. Now generally what happens is when events are occurring together, you'll see that occurrence of one event has an effect of occurrence on the other event. For example, let us say if you have 2 twins, let us say Neeraj and Dheeraj, probability that Neeraj will go to school is dependent on whether Dheeraj would go to school or not, because they are coming from the same family. So there may be same kind of circumstances in the family which may lead both of them not attending the school. So how to talk about this concept of dependence or independence? So to understand this dependence, we'll introduce the concept of conditional probability of an event B given the information that A has occurred. We'll also prove 2 important theorems of probability theory, which are called theorem of total probability and the Bayes theorem. So that is all for this module, and thank you for your patience and have a great day.